Welcome to the program. I'm Jeff Schechtman. The great screenwriter William Goldman once said of Hollywood that nobody knows anything. I hope that we've learned by now that the same doesn't apply to science. Random as knowledge sometimes might be, it's safe to say that the entire technological infrastructure of modern society, all of Silicon Valley, for example, is built on top of the reliable functioning of the laws of mathematics and physics. The fundamental laws of physics, which govern the workings of the cosmos, are not some abstract, untethered set of rules. They have a direct impact on how we live, on the very meaning of human existence. It has to. After all, it's the only way we can look out at the vastness of space and time and ask ourselves what it's all about and what's our place in it. Few understand this better and are able to explain it more clearly than my guest, Sean Carroll. Sean Carroll is the Homewood Professor of Natural Philosophy at Johns Hopkins University. He's a member of the Fractal faculty at the Santa Fe Institute. He's host of the Mindscape podcast, and he's the author of numerous books about physics and philosophy. He's been awarded prizes and fellowships by the National Science Foundation, NASA, and the American Institute of Physics. He's one of the most trusted explainers of some of the mind-boggling concepts that have for too long cloaked the most valuable building block of modern science. It is my pleasure to welcome Sean Carroll back to this program to talk about his newest work, The Biggest Ideas in the Universe. Sean Carroll, thanks so much for joining us.
Thanks for having me, Jeff.
Well, it's great to have you here. Have we lost some of our wonder as a society about some of these scientific concepts, about the cosmos, and about our place in it?
I would say that most people actually have quite a bit of wonder about the cosmos. I think that in our discourse, in the conversation that we have in the public sphere, that doesn't always come across. It's considered like a little bit scary, a little bit abstract. Maybe it's not really very relevant to everyday concerns. But I think that most people really want to know how the universe works. You tell them about the Big Bang and black holes and particle physics, and they want to hear more.
What about when you introduce the element, and you talk a lot about this in The Biggest Ideas in the Universe, when you introduce the element of mathematics, and that's part and parcel in so many ways of understanding this?
Well, I think it's an interesting issue because we tend to divide people up into two different buckets. One bucket is you're an amateur. You don't know the math. You don't know the physics, but we can tell you stories about it. We can draw pictures and you can learn things. And that's what I've done in my own books so far. And then we say, you're a professional. You're a physics student. You're going to take years of courses. You're going to do a lot of homework. You're going to take final exams. You're going to learn all the math. And I think that there's just too big of a gap in between there compared to what there should be. I think there's no reason to hide the secrets of the mathematics of physics from people who don't necessarily want to be professional physicists, but are still very interested in it. The math is not nearly as intimidating and inaccessible as we make it out to be.
Talk a little bit about that and the ways things like geometry and algebra and calculus play into understanding all of this.
Well, this is something that goes back to, I guess, what we would call, what I keep calling the birth of modern physics, even though it was in the 1600s. So I don't know if you want to count that as modern or not. But when people like Descartes and Galileo and Newton put together the rules that we currently call modern physics, their big step forward was realizing that physics is very simple at heart. We can take away complications. Like Galileo, for example, famously said, a heavy object and a light object will fall at the same rate if there were no air resistance. And that sounds like pretty easy to say, but, there is air resistance. So what gave him the right to say that? And the answer is that once you say that, you can attach very specific, rigorous quantitative equations to the motion of objects in the universe. And then you can always put back in the air resistance and other complications. But these equations are smarter than we are. They make predictions that we human beings wouldn't have gotten to if we weren't forced to believe what the equations were telling us.
Talk about the ways in which it's important to keep in mind, I think, the fact that these laws, these rules, these equations are so much a part of the fundamentals of the technology that we interact with and use every single day.
Yeah, and I think that me personally, I like to be very upfront about the fact that although physics in particular and other sciences generally are crucially important for technology. That's not why I'm interested in them. I just want to know how the world works, right? If we know what dark matter is, which we don't yet, but we're trying to discover it, that actually probably won't be helpful for technology, but it'll be an enormous clue about the fundamental nature of reality, which is pretty cool. And the ability to understand that at the level of the equations, I think, gives you a different way of thinking. It's like being able to play a musical instrument or speak a foreign language. It's accessible to anyone who wants to put in the work. And then once you get there, you have a kind of knowledge you couldn't have any other way.
Does the practical side of it, or understanding the practical side of it, though, help kind of spread the gospel? Does it help make people more interested in understanding these concepts of physics?
Oh, yeah. I mean, no doubt. The great thing about being a physicist since the 20th century is everyone agrees it's important, right? You could not come through the 20th century without understanding that physics is very, very relevant to our human lives. It is greatly appreciated, affected our not only ability to build technologies that we all know and love, but to do things like go to other planets or to imagine building settlements on Mars or the moon or something like that. If we didn't know about the physics of the planets moving around in the solar system the way they do, we wouldn't be able to do this. The famous example is Albert Einstein's theory of general relativity, which he came up with in 1915. Nobody thought at the time it would have any technological application whatsoever. But it turns out that our GPS systems would not work if we didn't understand general relativity. So literally, when I ask Google Maps how to get from one place to another, Albert Einstein is helping me get the answer.
Talk about the speed at which things are changing, the speed at which knowledge is being acquired, and the necessity sometimes to keep up with that. And yet, for some of the fundamental ideas and the fundamental physical concepts that you talk about in the biggest ideas in the universe, these are things that have been known and sound for quite some time.
Well, yeah, and I think that's a very interesting and complicated question because, number one, knowledge is advancing very quickly. There's a lot of people out there who are very smart, doing scientific research, doing experiments, teaching us things. We're learning a lot. Number two, the rate at which knowledge is advancing is kind of unpredictable. It's going forward, but different fields move at different rates. This is very simplistic, but a lot of people say that the 20th century was the century of physics and the 21st will be the century of biology, because we're really making advances in biology these days in a way that we weren't 100 years ago. And the third thing is there's progress and then there's productivity, which are different things. So people will continue to write scientific papers and come up with new ideas, whether or not they represent large advances in our knowledge. So if you're a working scientist, the thing is you don't know whether someone's paper is going to be really, really important down the line. So there's a flood of information out there that we have to struggle to keep up with.
In trying to grasp all of this, talk about the fundamental places that people need to start from in terms of understanding the physics, the grounding that they need first.
Sure. In my books, The Biggest Ideas in the Universe, the whole point is you don't need to know any math at all coming into it. Now, to be fair, maybe understanding 2 + 2 = 4 would be very helpful, or at least, E = mc squared is a very simple equation that I think people can understand very basically. But we start with the simplest idea of conservation. That's chapter 1. And conservation is just the idea there are some quantities that don't change at all over time. Energy is constant. What that means is you can change energy from one form to another, but the total amount stays the same. Momentum is the same from moment to moment. And that turns out to be super profound. It's not at all obvious. Aristotle would have been shocked at the idea that energy or momentum are conserved. It's really a new angle on understanding the universe. But then building up from there, you start looking at things that do change, what it means to move through space. What is space anyway? What is time anyway? And before you know it, you're doing general relativity and discovering black holes.
What about calculus? How important is that in understanding all of this?
Well, calculus is the major player, honestly. That's the one kind of math that probably most people are not comfortable with that you really, really need to understand modern physics. So, in the book, my attitude is great. We're going to teach you calculus. And the thing that makes that possible, despite maybe you have recollections of high school nightmares of doing calculus problems or something like that, or even not even taking the course because it sounded too intimidating, is that we're not giving you homework. We're not trying to make you solve problems. What we want to do is to help people understand the basic ideas. And that turns out to be much, much easier than solving equations. You can understand the equations without spending a lot of time trying to solve them yourselves. So calculus is just two ideas. One idea is how fast are things changing? And the other idea is how much change has happened over time. The first idea is called the derivative, the rate of change. The second idea is called the integral, the total amount of change. And Isaac Newton put these ideas to work to describe the motions of planets around the sun. You start from one point. Here's the planet. It has this location. It has this velocity. It's being pushed around by the sun. Where does it go? And calculus answers that question and continues to be useful as we discover more and more of the laws of physics.
And when we look at those laws, it seems that there really are three principal areas that we're looking at that relate to each other, which are these ideas of space, time, and motion.
Yeah, I think that's one of the things that we learn throughout the history of physics is not only do we answer questions, but we learn what are the good questions to ask. So back in, again, Aristotle's time, the idea of time seemed a little bit mysterious. We had the universe, and we would have called the universe all of the stuff in the universe located in space at different points of space. And then time is some kind of process, some way of describing change that was a little bit mysterious. And it built up over hundreds of years through the work of Galileo and Newton all the way up to Einstein to realize that space and time are similar to each other. They're both ways that help us locate things in the universe. If you want to meet someone for dinner, you need to say where you're going to have dinner and also when, right? Those are two pieces of data you have to give them. And this culminates in Einstein's theory of relativity, where in fact there is just one unified idea of space-time, and different observers in space-time will divide it up differently into space and time. And that's the modern view we go forward with.
And what is the cutting edge now of understanding this? What do we know now that Einstein didn't?
Oh, that's a great question, because I'd like to brag a little bit that I know more about general relativity than Einstein did, despite the fact that he invented it. Of course, it's not really bragging. It's just that I was born later than Einstein, and we have learned a lot since Einstein came along. So in 1915, he puts forward his equation for general relativity, and it's an instant success. He understands an existing anomaly in the orbit of Mercury. He predicts deflection of light by the sun, which is then observed very, very quickly, and he becomes a world-famous celebrity. But there's a lot hidden in that equation that he didn't know about. I mean, one is just the existence of black holes. Einstein went to his grave never knowing about black holes. Something he did learn about later was the Big Bang theory, right? The idea that 14 billion years ago, the universe was hot and dense and rapidly expanding, and it cooled off into the universe we see today. The idea of gravitational waves going through space, all of these different phenomena were not on Einstein's mind when he invented the theory. But the great thing is they were there in the theory, despite the fact that Einstein didn't know it. The theory knew more than he did.
And talk about black holes and why there is such a fascination with them today, and what we really are seeking to learn from them.
Yeah, like I said, black holes were always lurking there in the equations, but it took us a long time to really appreciate it. So Einstein writes down his theory in 1915. Just 2 years later, in 1917, Carl Schwarzschild solves Einstein's equation. And it's a great story because Schwarzschild was in the German army. World War I was going on at the time. And he was a trained astronomer, so they put him to work calculating the trajectories of artillery shells. But in his spare time, he learned general relativity and solved the equations. And we now call his answer the Schwarzschild solution. It's what describes gravity right here in the solar system. But there was this special feature of his solution that if you crushed enough mass into a sufficiently small region of space, some kind of threshold was crossed. And it was a weird thing. And they didn't understand it. And they talked about it. They're like, what happens at this point? It's really weird. We don't know. It wasn't until the 50s and 60s that scientists finally understood what was going on, which is a black hole, a region of space where gravity is so strong that nothing can escape, not even light. And that was thought to be kind of a mathematical curiosity. These days, we look at black holes all the time. We see their effects. We see the black hole, or what we really see is the matter spinning around the black hole at the center of our galaxy. It's 4 million times the mass of the sun. We can take a picture of it. Other black holes spiral together and give off gravitational waves. People can detect that and they win the Nobel Prize. So black holes have become absolutely mainstream in astronomy, even though they were implicit in the equations 100 years ago.
And what do they tell us about the cosmos beyond the uniqueness of and the curiosity that they are?
Well, I think it's interesting both for relatively down-to-earth astronomers because black holes play a role in the evolution of stars and galaxies and maybe other things in the world. So our galaxy has a black hole at the center, like I said, 4 million times the mass of the sun. You might think that in some sense that black hole is holding us together, but that's not exactly right. The galaxy has 100 billion stars. So in fact, the black hole is kind of tiny compared to the galaxy, but it might play an important role in the history of the galaxy. We look out at older galaxies and they're often very, very brightly shining. And we think that's because that's part of the process by which the black hole was formed in the early universe and all of the gas and dust spiraling into it, glowing as it spirals in and giving off this huge amount of radiation. So for astronomers, black holes play an important role in the evolution of the universe. For physicists, black holes are fascinating because they're extreme, right? It is impossible to squeeze more energy into a region than a black hole has. And that makes them playgrounds for the minds of theoretical physicists. We're still trying to wrap our brains around exactly how black holes work in the real world.
And one of the things that you often add to the discussions of this, in The Biggest Idea in the Universe and in other things you've written, is the broader philosophical framework to understanding all this beyond the science. Talk about that.
Yeah, I do think that there's been a long history of an interplay between philosophy and science in general, physics in particular. I mean, there wasn't in Isaac Newton's time any difference between philosophy and science. Newton described himself as a natural philosopher. And later things sort of splinter off, and then partly that's just because of academic politics and things like that. But it remains true that there are some issues in science for which a philosophical cast of mind is very helpful. The idea that we can be patient, we can think things through, ask the most fundamental questions, ask why things are this way rather than that way. And so for these books, mostly I want to talk about ideas that are established, right? We're not speculating about extra dimensions or the multiverse or whatever. But I do like to lay out some of the philosophical underpinnings because eventually we will want to move beyond what we currently know. And I think that task is greatly aided if we understand what we're doing. And that means knowing a little bit of philosophy.
And concurrent with that is imagination and the way that that's part of both.
Yeah, no, absolutely. I mean, science is a creative endeavor. And the part of science that we understand the least is how people come up with new theories, right? That's part of the scientific method. You have to come up with a hypothesis and then you test it. But nobody knows how to do that. Good scientists are good at it. We don't know how to program a computer to do it or anything like that. So that task of imagination is to say, well, maybe things could be this way, maybe they're that way. What are the important ingredients? How do they fit together? How do we simplify what's important and ignore what's a complication? All of that is what goes into making a really good theoretical physicist.
And talk about quantum physics and why that's important. It's an area, again, that people hear a lot about, sort of fascinated by, but don't really understand in many cases.
Yeah, well, that will be book 2
Right.
of the series. This is book 1 of a 3-part series. And the first book is all classical. The second book is quantum. And this was the great revolution that happened at the beginning of the 20th century that we sort of put together in the 1920s. And the idea is that if you look at atoms, look at radiation, look at all these tiny little phenomena, the ordinary rules of Newton or Einstein make predictions, but those predictions are just wrong. They're not how nature really behaves. And people eventually realized that it's a very, very deep thing. What nature is at the fundamental level is not a bunch of particles interacting through forces. It's a wholly different kind of thing, which we call the wave function. And we don't need to get into what the details are. But what's relevant about it is, unlike in classical physics, where you can set the system up, whether the system is the universe or a pendulum or whatever you want, and then you can predict what it will do. In quantum mechanics, you can set the system up, predict what it will do, but you cannot observe what it's done. All you can predict for your observational outcomes are the probabilities of getting different answers. You can never predict exactly what you will observe. Quantum mechanics has some special place for the act of observation that classical physics doesn't. And honestly, we still don't understand this. Like, some of us have ideas that we are very attached to, but there's not a consensus. There's not an agreement on what's going on, why observation and measurement are so important in quantum mechanics, though they're not anywhere else. But what we do know is it works. For whatever reason, this crazy ad hoc set of rules that we have in quantum theory really fits the data very well.
One of the things that it seems you're saying is that in the realm of quantum physics in particular, that we're still learning. There's still so much that we need to understand, and certain things that we think today might be proved wrong or right as time goes on. Coming back to this book and classical physics, are those all settled ideas at this point?
I think that most of the things I talk about in this book are settled ideas. And indeed, even in the next book, in quantum mechanics, I'm going to be talking about the parts of quantum mechanics that are settled, right? There are certain parts of it that are pretty well established. But in both cases, classical or quantum, it's not hard to put your fingers on remaining mysteries. So in this book, for example, I talk about the nature of time. You know, is time eternal, or is it just a moment to moment kind of thing? Why is there an arrow of time? And, you know, that's still a bit of a mystery. What is the nature of infinity? Is the universe continuous fundamentally, or is it discrete? So I don't dwell on all the different possibilities, but I give little signposts letting you know, because one of the big goals of the book is to prepare you for future advances. When we learn things, you'll be able to go, oh, yes, I see where that fits into the physics that I've already known.
And talk about the third book. If the second deals with the quantum universe, what is the third one going to deal with?
The third one is called Complexity and Emergence. So the third book is where we admit that there are interesting systems in the universe that have more than just 2 or 3 particles to them, which is what we're usually doing in the first 2 books. Right. The universe often has situations where there are many, many moving parts that come together at once, whether it's the universe as a whole, or a box of gas, or a living cell, or an economy, or something like that, right? Complexity and emergence are what happens when you're able to say something sensible about a system, even though what you're able to observe about it is only a tiny fraction of what's really going on. There's all sorts of little moving parts underneath the hood that you don't know about, but nevertheless, you're able to capture some of the essence of what's going on. And to me, that's actually one of the most interesting and fascinating areas of modern physics.
And it's funny that you say that, because what I was going to ask you is, what are the things that are most exciting to you at this point?
Well, that is one of them. I think the 2 things that are most exciting to me are, number one, the evolution and nature of complexity in the universe. Like, physicists are really good at understanding systems that are simple. A pendulum swinging back and forth, a planet going around the sun, even a black hole is simple. Like, the equations might be intimidating, but at the end of the day, there's not a lot of moving parts inside a black hole. It's just a single thing sitting there. when things come together, new things become important. More is different, as the physicist Philip Anderson once put it. And we're still trying to understand that. So it's exciting to me, not just because it's intrinsically interesting, but because there's a lot of questions that are easy to ask but hard to answer. The other one is truly understanding quantum mechanics and its relationship to space and time. We have this huge hole in theoretical physics where we can't reconcile our understanding of space-time with our understanding of quantum mechanics. So that's something I would like to make progress on.
Sean Carroll, his new book is The Biggest Ideas in the Universe. Sean, it is always a pleasure. I thank you so much for spending time with us.
My pleasure. Thanks for having me on.
Thank you.